Vibration in buildings mainly considers vibration of rotating equipment and impact vibration. Vibrations from rotating equipment are transmitted to the building structure through the equipment foundation. As vibration propagates through a building structure, the frequency remains the same, and the vibration intensity may increase or decrease. When resonance occurs, the vibration increases, and in severe cases, damage equipment and structures. The rotating equipment and its equipment base form a vibration unit, and the vibration unit has a natural frequency. When the equipment starts, the rotation frequency gradually increases from static to steady state frequency. When the equipment is stopped, the rotational frequency gradually decreases from the steady state frequency to the standstill. If the resonance frequency is larger than the steady state frequency, when the equipment starts and stops, the rotation frequency will be the same or close to the resonance frequency and resonate within a short period of time. The resonance frequency region is called the resonance region. The start and stop of the equipment need to pass through the resonance area quickly to avoid excessive vibration due to resonance. The characteristics of impact vibration are short action time, large vibration impact energy, and raised frequency components. The vibration near the natural frequency is transient and more radiated into the air, forming air sound. This graph is a frequency characteristic of vibration transmission. The abscissa is a frequency ratio, which is equal to the ratio of the vibration frequency of the equipment to the natural frequency of the vibration unit. The alternate is the transfer coefficient, also known as the transmissibility, which is equal to the ratio of the amplitude transmitted to the foundation to the amplitude of the vibration of the equipment. The values on the different curves in the figure are the damping ratios. When the frequency ratio is less than the square root of 2, the transmission coefficient is greater than 1, and the vibration transmitted by the equipment to the foundation is greater than the vibration of the equipment itself, which is the vibration enhancement area. When the frequency ratio is equal to the square root of 2, the transmission coefficient is equal to 1. The vibration transmitted by the equipment to the foundation is equal to the vibration of the equipment itself, and the vibration is transmitted without attenuation and without vibration isolation. When the frequency ratio is greater than the square root of 2, the transmission coefficient is less than 1, and the vibration transmitted by the equipment to the foundation is less than the vibration of the equipment itself, with the vibration reduction area. Under a certain damping ratio, the larger the frequency ratio, the smaller the vibration transmitted to the foundation. When the frequency ratio is constant, the transfer coefficient increases with the increase of the damping ratio. It can be seen that the small damping at this stage is beneficial to the vibration reduction. When the frequency ratio is equal to 1, that is, when the frequency of the equipment is equal to the natural frequency, resonance occurs, and the vibration transmitted by the equipment to the foundation is the largest, but it decreases with the increase of the damping ratio. It can be seen that the large damping at this stage is beneficial to the vibration reduction. Therefore, the basic principle of vibration isolation is to make the vibration frequency of the equipment as far as possible greater than the product of the natural frequency at the square root of 2. When the vibration passes through the resonance region, the damping needs to be increased to prevent short-term excitation. It can be seen from the previous discussion that the greater the frequency ratio, the greater the vibration reduction efficiency. Since the vibration frequency of the equipment generally cannot be changed, it is necessary to reduce the natural frequency in order to improve the vibration reduction efficiency. Since the natural frequency is related to the weight of the object and the elasticity of the support, it is possible to use a softer spring or increase the weight. Increasing the weight of the base of the equipment is a common method, since too soft springs can cause the equipment to tip over. The impact sword is excited by direct impact on the outside of the enclosure structure of the building space. What is received is the air sword radiated by the impacted structure into the building space. Hit the floor with the international standard striker. The room under the floor is the use room for field measurements, and a fixed value vibration room for the laboratory. Measurements require sound pressure levels in the 1/3 octave band in the range 100 to 3150 Hz. The higher the normalized impact sound level obtained, the worse the impact sound isolation effect of the floor is. Similar to air sound insulation, the 1/3 octave impact sound insulation reference curve is used. This is superimposed with the spectral curve of the measured quantity, a single evaluation index. The weighted normalized impact sound level is used to impress the impact sound insulation performance of the component. The smaller the LPN.W, the better the impact sound isolation effect of the floor. Plot the measured amount of impact sound insulation in the 1/3 octave band equal to 0.1 dB as the measured amount spectrum curve in Figure A, and cover the 1/3 octave band impact sound insulation reference curve in Figure B with the same coordinate scale to Figure A as shown in Figure C. The abscissor is overlapped, and the 0 dB of the reference curve on the ordinate is aligned with a certain integer coordinate of the frequency characteristic curve of sound insulation. Move the reference curve 1 dB each step until the sum of the value of the frequency characteristic curve of the measured quantity in the same frequency band is higher than the reference curve as much as possible, but not more than 32 dB. At this time, the integral decibel of the ordinate on the frequency characteristic curve of the measurement quantity corresponding to the 0 dB line on the reference curve is a single value evaluation quantity corresponding to this group of measurement quantities, and its abscissor is 500 Hz. It can be seen from Figure C, corresponding to 100, 125, 160, 200, 250, 2000, 2500, 3150 Hz. The values of the measured frequency characteristic curve larger than the reference curve are 7, 6, 4, 3, 1, 2, 2, 1. The sum is 26 dB. At this time, the intersection of the two curves is the intersection of the reference curve 0 dB and 500 Hz, and the value of the ordinate on the frequency characteristic curve corresponding to the measured quantity is 58 dB. That is, LPN.W is 58 dB. According to the building sound insulation evaluation standard, it can be seen that the impact sound insulation performance of this component is 4 grades, and there are 8 grades in total. According to the cause of the impact sound, the isolation measures for the impact sound can be obtained, mainly including 1. Attenuate the vibration caused by the vibration source hitting the floor, including controlling the vibration source, taking vibration isolation measures, and laying an elastic surface layer on the floor. Vibration isolators and vibration isolation components commonly used in vibration equipment mainly include metal spring vibration isolators, rubber vibration isolators, rubber vibration isolation pads, glass wall boards, and rock wall boards. The surface material is commonly used carpet, rubber, plastic, wooden floor, etc., which can greatly improve the medium and high frequency. Increasing the thickness and softness of the material will also improve the low frequency. 2. To block the propagation of vibration in the floor structure, a floating floor with an elastic cushion layer is usually used between the floor surface layer and the load-bearing structure. 3. To block the air sound radiated by the vibration structure to the receiving space. It is usually used as a sound insulation ceiling under the floor. The impact sound improvement value was used to evaluate the effect of the isolation measures. The improvement value is equal to the difference in normalized impact sound level before and after the action is taken. You can find information to learn about the practice of the room, within the room, and the sound log. And you can also go to the equipment room to see what vibration isolation measures have been taken. Feel the vibration isolation and sound isolation for yourself. And you can also compare the sound isolation difference between an old building with solid bricks and a new house with hollow bricks. When sound waves pass from one medium to another, reflections occur at the interface between the two media. The reflection coefficient is equal to the ratio of the reflected sound energy to the incident sound energy, and can also be obtained from the density of the two media and the sound speed of sound wave propagation. The design of the wall and ceiling needs to control the reflection coefficient and reflection direction. Common directions are directional reflection and diffuse reflection. Directional reflection reflects the incident sound wave in a specified direction, satisfying the loss of geometric reflection. The reflective surface is generally a plane or reflective surface with a certain geometric shape. The dimensions of the reflecting surface are much larger than the wavelength of the sound wave. Diffuse reflection reflects incident sound waves in all directions, satisfying the law of geometric reflection. The reflective surface is irregularly and randomly undulating, and the magnitude of the undulation is comparable to the wavelength of the incident sound wave. When the fluctuation scale is smaller than the wavelength of the sound wave, although the geometric reflection law is still satisfied, diffusion will not be formed. The diffuse reflection surface can be designed to have regular undulations. An undulating diffuser can be installed on a flat wall. The relationship between the size of the diffuser and the wavelength of the sound wave can be estimated. The reflective members are required to be thin and have a smooth surface. Think about it. Is there any difference between diffuse reflectors used in multi-purpose halls, where meeting and performance are often alternated, and single-function rooms? How to combine diffuse reflector with architectural decoration?